Hello, thank you for watching this video. I'm Tao Chen from Loughborough University, UK. Today I'm going to present our work on planning landscape analysis for self-adaptive systems. So many software systems will come with different configuration options to change even a runtime, and this can affect the performance. And here I show an example of this kind of software systems. As you can see, they have a non-trivial amount of configuration to explore, which is kind of challenging. But here the challenge is that finding the best configuration before the deployment is really hard because the environments, for example, the workload that the system encounter can be uncertain and may always be changing. And this is an example of the system Apache Storm. As you can see, at runtime, if you receive different kind of jobs highlighted by different colors, and that represent that these kind of jobs will come from different types or different loads. And if you apply a fixed configuration, the consequence is likely to be that the performance keep varying, and very likely it doesn't satisfy what is required in terms of the non-functional attributes. Therefore, the above scenarios motivate us to think of highly configurable systems as self-adaptive systems. Thus, because they can change their adaptation plan. In this context, will be the configurations in reaction to various different environmental changes, such as the time-varying workload. And often here, what we're trying to do, we are interested in optimizing and guaranteeing certain performance concern, such as latency and throughput. So that brings to our SAS planning problems. What is the next best adaptation plan under changing environments? But what is missing? Well, we know that designing effective planners for SAS is challenging because while the search space could be large, in some occasion it could be a few hundred thousands of possible adaptation plans. Also, the budget for a planner to conclude and terminate could be limited because of dealing with a runtime scenario. Also, there may be complicated relationship between adaptation plans and their performance, as well as the changing environments. For example, there could be interaction between the adaptation options, and also the same adaptation plan may change significantly under different environments in terms of the performance. So over the past decades, there has been various different planners proposed for SAS. For example, Plato, Fusions, Fimosas, and more recently, the one with seeded genetic programming. But the key missing bit is that it remains unclear about what characteristics of the SAS planning landscape that have enabled their success or failures. Of course, a straightforward way to answer the above questions would be just to plot and visualize the landscape, which is what commonly has been using in existing work. So here I shows two examples of the landscape under two different environments for Apache Storm. Well, here we see that we can see some local optimal there. So these are the suboptimal points that's better than the neighboring adaptation plan, but still they're far away from the true global optimal, which is indicated by the dot here. Well, if you just visually inspecting the landscape, we could see, well, there may be some similarity in terms of the shape, uh, but at the same time, there are some differences for which it's difficult to tell. So that immediately bring up to the limitation of this kind of visualization in terms of analyzing the planning landscape, and that is they are limited to three dimensions. So here can only plot three dimensions. If I put the fourth dimension in, it will be much more difficult to interpret. And again, it's difficult to understand and interpret what exactly the differences and similarities are. That is because they are hard to quantify, and therefore we cannot conduct comparative analysis on the landscape between different environments. So the question here we really would like to answer with planning landscape analysis for SAS are things like, does the correlation between performance and plans are really useful for planners? So whether this kind of special shape can guide a planner towards reaching a better plans. And also a question like how rugged the surface is. Can we quantify the ruggedness of this kind of shape? And what sort of properties of the landscape that has been changed or even unchanged between different environments? So these sort of questions are what we try to answer by using techniques and notions that we use in this particular work. So in these papers, our contributions are that we show how the metrics and notion from the well-established domain of fitness landscape analysis can be derived to study planning landscape for SAS, particularly in relation to different environments. And we also conduct an empirical analysis for 4 real-world SAS with 14 different environments from the literature, and the key question we try to answer are that do the planning landscape offer useful guidance to a SAS planner under different environments? And what are the general structure properties of planning landscape of SAS under different environments? And that is particularly related to their modality, their ruggedness, and so forth. And we're also interested to understand, do the local optimal being closer to the global optimal than the other non-optimal points? So whether they could be helpful for us to reach better plan if we try to preserve them. And finally, is it possible to share some information of the landscape for SAS between different environments? So these are the 4 research questions that we will provide answers for through our empirical studies and the techniques and notion we use. So to start with, we could provide a simple formulation of the SAS planning problem where we try to find the minimize x vectors for these particular functions, where function f is a performance we try to minimize, and x is basically the adaptation plan, and a big X is the search space of all the plan. And then we can design in the planning landscape in terms of mathematical functions. It could be represented by a tube with a bx, f, and nx, where the nx denotes the neighboring plans of a particular point in the search landscape, and the k depending on how much further we want the neighbor threshold wants it to be. This is an example of the planning landscape where the neighbor of a particular point is kept by a particular length of k. So basically, if you can see from here, the landscape it's a combination of different neighbors, which may or may not be overlapping. So for defining the neighbor, we also need a distance metric. In this work, we use Hamming distance because of 3 reasons. Firstly, its sparse comparisons fit well with the nature of configurable SAS, and because it doesn't quantify the magnitude of differences on the adaptation options. As long as 2 plans differ on one adaptation options, then their Hamming distance will always be 1. And finally, is widely used in many real-world problems. And here we set that the distance differences of 1 is considered as a neighbor, and subsequently we can define a local optimum as a point that if it is no worse than all of its neighbors. So this is an illustration of all this concept where we see this little box L here, is a local optimal because if compared with the vertical um, bar and the horizontal bar, that these L is the best in terms of the Hyman distance with k equals 1. And of course, it's a local optimal because the point around here is much better than it, and that is the global optimal in this case. So the first notion we use to quantify the landscape is fitness distance correlations, which examine how close is the relation between fitness values and distance to the nearest optimal. So basically, it's a Pearson correlation between a point, its performance value, and its distance to the global optimal, and where a 1 and -1 imply the strongest positive and negative correlation respectively. So if we are minimizing the performance and if the two values change in the same trend, then we said that the guidance is very strong because once we reduce the distance to the global optimal, then we will get better results. Secondly, we could also quantify the structure of the landscape, and we use two metric. The first one is the multimodality in terms of the percentage of global and local optimal. So here is an example where we showed all these stars, I mean the peak, and these are the local optimals. However, only showing that we don't know the correlation between different local optimal points, and therefore we use another metric called correlation length to quantify the local roughness properties. So what we're doing here is we perform a random walk and we collect some points and we calculate the correlation between performance of these points so that we can have a correlations and a general idea about what shape that these sort of point form. And in this case, the higher the value of the correlation length, the smoother the landscape, and vice versa. So with all these metrics and notions in mind, we now perform our empirical studies using for real world SaaS with different environments that could changing around time. They're coming from different options and search space. And for the roughness, we use a random walk with a stat equals 1 and a walk length equals 50. And we repeat 50 times to correct the more stable results. For statistical test, we use Fisher transformation and those confidence interval for testing correlations and in RQ1 and RQ2. And then we use a non-pair Wilcoxon ring sum test for RQ3. So for the first research questions, we evaluate the fitness distance correlation across the systems. And here we use the interpretations from the original author of these metrics, where we say if the FDC is smaller than minus 0.15, it means that the landscape provides misleading information. Because when the distance becomes smaller, then actually the performance getting worse. In contrast, if the value is between minus 0.15 and 0.15, then we say the problem is difficult because the distance between the point to the global optimal actually provide no information about whether the performance is getting worse or getting better. In the final case, we said that the landscape offers very useful information because whenever you reduce the distance to the global optimals, then the performance will get better. And here we can see that across all the environments and cases, we have all the case with the rho of FDC greater than 0.15, meaning that the SaaS landscape indeed provide very useful guidance to the planner. And also, if we compare the differences of correlations between different environments, most of them are statistical significant. It means that well, when changing the environments, the guidance could change significantly. And therefore, we answer that the planning landscape offers useful and strong guidance to the SaaS planner in general, but environment change can influence the guidance provided. So next, we assess the planning structure of planning landscape, and for correlation length, we use three widely studied problems as the baselines. And here we can see from the left-hand side figure that the percentage of global and local optimal form considerable among the points in the space, and also between different environments, they tends to differ significantly. And if you look at the correlation length, you can see for all the cases, it has a smaller value than the most rugged problem from the three we consider here. And that means they are uh, rugged to a significant extent, which is difficult to tackle. If you compare the correlation length between different environment, we see that they aren't that significant statistically. So that led us to answer that the planning landscape for SAS show a good sign of multimodality, and they are more rugged than some other widely studied problems, yet the ruggedness is insensitive to the changing environment, but the multimodality does. So next, we assess the distance to global optimal with respect to the local optimal and non-optimal points. And as you can see clearly from these figures, for all the cases, we can answer the question as the local optimal are indeed generally closer to the global optimal than the other non-optimal points in the SAS planning landscape. And that means if we can preserve this local optimal and subsequently jumping out from them, then we are more likely to reach the global optimal. So finally, we try to understand three aspects about what information of the planning landscape can be shared between different environments. Firstly, whether there's at least one global optimal in one environment, there is also a global optimal in another. Secondly, whether there's at least one local optimal in an environment that become a global optimal in another. And finally, what is the percentage of global and local optimal overlapping between two environments? As if you can see from the table here, uh, for most of the case, it will be a yes for the first and second aspects. That means most commonly there will be at least one global optimal or local optimal that will be the global optimal in another environment. And finally, if you look at the percentage of overlapping on the global and local optimals, most likely they are tends to be very high. Um, that means our answer to this question would be preserving both the global and local optimals of the planning landscape in one environment can be very useful for such planning under changing environments. So here comes to our key insights from this work. So since the SAS planning landscape offer very good guidance to planner, they are particularly suitable for planner guided by fitness and drawn from one adaptation plan to another by taking the distance to the currently best adaptation plan into account. But the effect of guidance may change according to different environments. Secondly, we show that the landscape could be very rugged and difficult to deal with. That means mechanism which help the planner to escape from local optimal is indeed necessary, and also a mechanism that work for one environment will likely to work for the other too. And finally, we confirm again the importance of seeded planning and plan reuse for SAS under changing environments, as we show that there's a significant overlap in terms of the local and global optimals. But which one to preserve? Well, we believe that formulating multimodal planning for SAS could be a promising way to go, and this is what we have done as a recent work published senior this year. So in conclusion, in this work, we show how notions and metrics from fitness landscape analysis can be used to study the SAS planning landscape, and we use things like ruggedness and multimodality and the fitness distance correlation to do that. And we perform analysis on a set of real-world SAS from empirical studies, and our findings provide several key insights towards the future design of better planner for SAS. As a future work, we hope to provide some more dedicated methodology for analyzing the dynamic landscape planning in SAS, and also our observation can help to produce more specialized planners according to the properties and characteristics we show in this paper. Thank you very much for your attention.